Okay. How's everybody doing today? All right.
Different hat on today.
I know. I thought I'd switch it up a little bit. Yeah. So, So today we're going to start with a quick review of the receiver circuit. So this is the fiber optic receiver. We'll go through that. We'll talk about the stages. And then we will go on to our main topic for today, which is fiber optics. So fiber optics is all about sending information over optical cables. Oh, looks like we got some more toys. Oh, no. Oh, you got the big one.
Yeah.
Okay.
And it isn't the one I wanted.
So we'll start with a review of the receiver circuit, and then we'll go on and talk a little bit about fiber optics, what it is, why it's important, and how it works. And then we'll do a preview of today's lab. And spoiler alert, we're going to be working on our soldering projects more. Okay? So yeah, I know, surprise. All right, so let's start off with a quick review of the fiber optic receiver circuit. So this is the circuit. I should say that this is the circuit for most of the boards. There are a couple of other boards out there that have different revisions. And so be sure to check your revision number when you're looking at this schematic. I have posted, so this is for revision 2.2 of the board. I've also posted some other revisions for the, I've posted schematics of several other revisions on Canvas. So check that out and make sure that you're looking at the correct schematic for your board if you're trying to use it to troubleshoot or something like that. I made that mistake last time. I tried to use the wrong version of the schematic to troubleshoot a different board, and it didn't work. So check that out. So anyway, the first stage that we have here is the power stage. It provides power for the whole circuit. It gets its energy from this 9-volt battery here, and then it feeds that power through these long rails to the rest of the board. So we've got a ground rail that runs all the way along the bottom of the circuit here, and a 9-volt rail that runs along the top, and then anything that needs power can draw it from those two places. In addition to the battery, there's a switch to turn the circuit on and off. There's a capacitor to provide any quick burst of energy that the circuit might need, and then there's also an indicator LED there to show you when the circuit is on. The input stage receives the light from the fiber optic cable, and it detects that using this component up here. Anybody remember what this component is called? Yep, it's a transistor, and it's a special type of transistor that is activated by light. So anybody remember the special name for this type of transistor? Phototransistor, that's right. This is a phototransistor. Normal transistors have a third wire coming in, and that's what controls the resistance of the transistor. But in this case, that's controlled by the light that is coming in from the fiber optic cable. So this is essentially a variable resistor, and it's in series with this other resistor. And we remember that when we have two resistors in series, that's a voltage divider. So we've created our own voltage divider here, and the voltage right in the middle should be about half of the total voltage if everything is working properly. And then when this resistance of the phototransistor goes up and down, it causes this voltage in the middle to go up and down as well. Now, this resistor down at the bottom isn't just a plain resistor, it's this special kind of resistor that has a third wire attached to it. And anybody remember what we call that type of resistor? Yeah, a potentiometer. That's right. And we said that if we slide this wire all the way up to the top, we would be getting the full signal here. If we slid that wire all the way down to the bottom of the potentiometer, it'd be connected to ground, and it would be at 0 volts. And then sliding this wire up and down the resistor gives us some amount of signal between 0 and full. So what was this potentiometer used for? Volume, yeah, exactly. This is the volume knob. So you slide it all the way up, you get the full signal, full volume. Slide it all the way down, you get no signal or silence. So this is the volume control here. But even when we have this all the way up at full blast, the signal is still very small, so we need to amplify it. So that's what this next stage does. So in this next stage, we use this 386 amplifier chip. It's specifically an audio amplifier that's designed to provide enough voltage and current to drive a speaker. So we take the small signal that's coming in from our input here, and then we amplify it to higher power level that's high enough to drive a speaker. And the speaker is over here on the output side. We said that a speaker is essentially a movable membrane that produces pressure waves that are sound. So when it moves out, it produces high pressure. When it moves back, it produces low pressure. And those changes in pressure are sound. And we make that move back and forth with electromagnetism. So there's a coil of wire on the back of the membrane, and then there's a permanent magnet behind that. And by passing electricity through that coil of wire, we create a magnet. And if we pass it through in one direction, it forces that magnet away from the permanent magnet behind it. It causes high pressure. If we run the electricity the other way, it becomes attracted to that permanent magnet, and it pulls the membrane back, and it creates a low pressure wave. So we're able to create these high and low pressure waves from this speaker here. But before we get to the output, we also have this filtering stage. This filtering stage allows some frequencies to go through, but blocks out or absorbs other frequencies. So we said, what's the very lowest frequency that you can have? What would a signal look like if it had a frequency of 0 hertz? Yeah, exactly. It's constant. It doesn't change at all. So, so would we want to have a constant, unchanging voltage applied to our speaker? No. No, we don't. And why not? Right. It wouldn't actually make it move. Remember, we want it to move back and forth to create the pressure waves that are sound. A constant voltage would just create a constant current flowing through there. It would just hold that speaker in one place and not make it move. What else might it do to that speaker? Well, the coil of wire on the back of that speaker membrane is essentially just a long wire. And what do you get if you put a wire from a voltage to ground? What do we call that? That's a short circuit. Yeah. So essentially, if you had a constant voltage applied to a speaker, you're creating a short circuit from that voltage to ground. And that's bad for a couple of reasons. First of all, it drains your battery, and also it heats up the wire. And that wire is glued right on your speaker membrane, so if that gets hot, it can burn right through your speaker. So for all of those reasons, we don't want to have a constant voltage on that speaker. So we want to cut out that very, very low frequency signal. And really, humans can't hear anything below about 20 hertz. So we might as well cut out anything below 20 hertz because we're not going to hear it anyway. So what we do with this filter is that we create a circuit that allows some frequencies to go through, but it blocks out or absorbs anything below about 20 hertz. So if we looked at a graph where we had voltage on the vertical axis and frequency on the horizontal axis, then we might want to set it up so that our filter allowed high frequencies to pass through, but then it blocked out or absorbed frequencies below about 20 hertz. And anybody remember what that type of filter would be called? Something that let high frequencies go through but blocked out low frequencies? Yeah. That's right. That's a high pass filter. So we want to have a high pass filter there so that we block out those low frequencies and we don't burn up our circuit. So this capacitor here, C4, and this resistor, they work together to create that high pass filter. Remember, the capacitors allow high frequencies to pass through them, but they block out or absorb low frequencies. So this capacitor and the resistor form a high pass filter, and they allow the high frequencies to go through to our speaker, but they block out and absorb the low frequencies. So that's good. But we also want to have, we want to block out the highest frequencies as well, because there might be things like radio frequencies and things above our hearing range, and we don't want to have those go through to our speaker. So we also want to have a filter that allows low frequencies to go through, but blocks out or absorbs the highest frequencies. And we can set this cutoff frequency to be something like 20 kilohertz, because that's about the highest range of human hearing. So we could have a low pass filter as well. So that's what this capacitor does. It allows the highest frequencies to go through that capacitor to ground. So the highest frequencies don't make it to our speaker. Lower frequencies cannot go through that capacitor, so they travel on towards our speaker. So we have a high pass filter and a low pass filter, and working together, they allow only the frequencies in the middle of this range to actually make it through to the speaker. So only the frequencies that are not blocked out by either filter make it all the way through. So there's only a band of frequencies that get through to the speaker. So together, these two filters make up something called a band pass filter. So that's what we have going on here in the filtering stage. So any questions about that? Okay. Did you have a question?
I have a question about the amplification statement.
Sure.
You said in the last lecture, I believe,
Yeah.
that C5, the 10 nanofarad capacitor,
Yeah.
affects the amount of amplification performed by the op-amp?
So this is, an audio amplifier, and the amount of amplification is determined by any resistors or capacitors that you put in this path here. Yeah. So the more resistance you put in this path, the more, or the less amplification it has. So what's actually going on with this capacitor here is that, remember we said that capacitors allow high frequencies to go through, but they block out or absorb low frequencies. So essentially, the lower the frequency is, the more resistance this capacitor has. So this causes the amplifier to have less amplification for very, very low frequencies, but more amplification for higher frequencies.
That's really neat.
Yeah, it's pretty cool. Thanks. Yeah. I wish I could say it was my idea, but it's all in the data sheet. So yeah, you just pick something off a list. Yeah. Yeah. Other questions? Okay. Cool. So that's a quick review of the receiver circuit. So then let's go on and talk a little bit about fiber optics. So first of all, what are fiber optics? So basically, fiber optics a fiber optic cable is a long, thin, clear cable that allows light to travel through it. And fortunately, Fred teaches a whole semester-long class about fiber optics. So if you hear something today and you get interested in it, I recommend that you take that class. Fiber optics is a really big technology. It's being used by AT&T and Comcast. They're making huge investments. They need people who can build fiber optic cables, and hopefully today you'll learn about why that is. So it's a really cool thing. I highly recommend it. But since Fred teaches that class, he's got all these fun demonstrations that show how this actually works. So you might wonder how this actually works. I mean, I said that a fiber optic cable is just a clear cable, and light shines down that cable. You might think, since it's clear, light would go in one side and just come right out. But actually, it doesn't quite work that way. What happens is that once light shines in the end, it actually tends to bounce around and stay inside that cable. So if you have a cable here and you shine a light in the end here like this, when it gets to the edge, you might think that it would just shine out, but it bounces off that edge and goes back, and then it hits another edge and bounces off, and like this, and then eventually it comes out the other end. So I have a big fiber optic piece of clear plastic here. Let me see if we can actually see an example of this. So I'm going to shine this in the end of the glass here. Can you see it bouncing off of the edge of the glass a little bit? Yeah. So that's what's going on. This laser that I have is actually a diffuse laser. So that means it spreads out. So it's a little bit harder to see. But if this were a more focused beam, it would be even clearer, and you could see exactly where it goes. But that's the idea. So when light shines in one end, it just bounces off the edges and it keeps on going. Let's see if we can do this way. Yeah, you can kind of get a sense for it that way as well. I'm going to try and not hit anybody in the face here.
What kind of material is that?
I think that it's some type of plastic. I'm not sure exactly what kind of plastic. This can even work when the material is not straight. So we have a sort of a curvy piece of plastic here, but the principle is exactly the same. So if I shine the light in the side here, you can see it still bounces around back and forth inside of that structure, and it comes out the other end. So this is the way that fiber optics work. You shine the light in one end, and it just stays inside of that material until it comes out the other side. So that's really what fiber optic cables are. They're just long, clear fibers that carry light from one place to another. So that's what they are. They can be made of different materials. The ones we use in class are made of plastic, but the ones that are used in industry are glass. So there's a couple reasons that we use plastic. First of all, it's cheaper and it's easier to work with, and it's less hazardous because if you have a very small piece of cut glass, it can be sharp and you can stab yourself with it. So we use plastic because it's cheaper, it's easier to work with, and it is less hazardous. But the downside to plastic is that it won't carry the light as far. So the plastic cables that we use in class might carry the light, a couple hundred yards, which is still, a decent amount. It's far more than we need, but it's not as good for trying to carry a telephone signal from one neighborhood to another or something. The industry types of fiber optic cables are made of glass. So this is a fiber optic cable that has been made of glass. And you can tell that this is not like glass that you've seen in a window pane, right? Imagine if you tried to take a glass from a window pane and bend it around in a circle. Would that work? No. So it's not exactly the same, but it's the same chemical composition. Okay? This is the same chemicals, the same material that we have in glass like we have in a window. The difference is that fiber optic cables, the glass for fiber optic cable is grown in one very, very long crystal. Or it starts out as a large crystal, and then it gets stretched and stretched to make it very, very long and thin. And what that does is that it leaves no tiny cracks in the glass. And when there's no tiny cracks, there's no place for a crack to start. And so it's possible to bend the glass without fracturing it and splitting it into 1,000 little pieces. So the glass is the same material, the same structure as you might find in a window or anything, or a wine glass. It's just grown in a different way. Okay? Yeah.
Does that process work with other material too? If you were able to theoretically be able to make it so there's no micro cracks, you could do it with like other material like metal, or like some sort of dense metal, but like if you were to do that process, could you?
I don't know. I'm not sure. Yeah, that's a good question. I have to take a look. Yeah. I know that the same type of process is used for silicon when people make chips, because it creates a very, very pure substance without any extra impurities or dirt or anything like that. So it's a similar process, but they don't stretch those crystals as far. So that's what fiber optics is. So why is it important? Well, like I mentioned earlier, fiber optics is being used all over the world, and it's being used by data carriers. People are, everything from phone lines to cable TV to internet is going over fiber optics now, and it's all. Even things like traffic cameras and streetlights are controlled by fiber optic. So you might wonder why. Well, this is a cable that used to be used to carry a lot of information. Okay, so this is a cable that would be used by the phone company. It has 640, it's got. Actually, I think it's got maybe thousands of pairs of these wires here, and it's just really big and really bulky and really heavy. Okay? Compared that to the fiber optic cable, you can see it would be a lot easier to work with these fiber optic cables, right? But you might wonder how many fiber optic cables it takes to equal the data carrying capacity of one of these big cables, right? Turns out that it would take 640 of these big cables to equal the data carrying capacity of one of these things, okay? So that's why everybody is going with fiber optic now. It's so much easier to do it, to work with those little things and repair them, and it's much less expensive. Okay. Yeah. Right. Yeah. It's no little thing. So fiber optics is everywhere just because it's so much easier to work with, and it's less expensive, and it carries so much more data. So I have a friend who works for AT&T, and he said that their biggest investment in 2023 is in fiber optics. That's where they're putting the most money, is putting fiber optic cables in. They're trying to get cables, to people's houses now. For a long time they've been using them to carry data, across the oceans and from city to city, and even into neighborhoods. But now they're trying to get them all the way to people's front doors. So it's a big investment for them. So basically, and the same goes for lots of other companies. So that's why fiber optics is so big now. So how does it actually work? So we talked about the light bouncing around and shining through a cable. Turns out that there are different types of cables. So one type of cable, the older type of cable, is called multi-mode. So a mode is one path that the light can take when it travels through a fiber optic fiber. So multi-mode means multi-path. So basically what that means is that you have a thicker cable, and if you shine the light in one way, it could take one path. If you shine the light in another way, it could go and take a different path and come out the other side. Now, it might sound like multi-mode would be a good thing, but actually it's not. And the reason is that when you shine your light in, you're creating a bunch of ones and zeros, ons and offs. So when you shine the light in and you turn it on, you want all of that light to get to the other side of the cable at the same time, so that at the other side it detects a quick change in brightness, and it says, okay, that must be a 1. When you have multiple paths that your light can take, then some of it might take a short path and get there quickly. Other parts of the light may take a longer path and get there in a longer amount of time. So instead of having a bright flash of light that comes on all at once, your light takes, kind of, some of it gets there and then a little bit more and a little bit more, and it sort of comes on more gradually. And that's bad because that takes more time to register that you've received a 1, and basically you can't pack in as much data that way. So newer cables are thinner, and they are called single mode. So single mode cables are thinner, and they make it so that you end up with all of the light taking the same path, and so all of the light gets to the other end at the same time, and therefore you end up with a quick transition from dark to light and vice versa. So you can get those ons and offs flowing through there very quickly, and therefore you can pack more data into your cable. Okay? Yeah?
How do you get multiple lights to shine from the same location?
Well, you mean like when I'm talking about multi-mode here?
Well, no, for the single mode, because you said you have multiple lights shining going down the same path. How?
No, what I mean, what I meant is all of the light from your laser shines down the same path.
Oh, okay. So okay.
Right, but it is actually possible to shine several different lights down a single cable. And yeah, so the way that they do that is with mirrors. So you have like you can have different colors of light shining down one cable, and then you can filter that at the other end and only retrieve a single color. So if you have 3 different colors of light, you can essentially be packing 3 times as much data down that cable. And they do that with mirrors. So you have partially reflective mirrors here. So you could have one beam of light that is starting here and then bouncing there, and then off of a partially reflective mirror and going down your cable. And then you could have another mirror over here and do the same thing with a different color light. So you could have a blue light over here. And then that is able to pass through this partially reflective mirror and also go down your cable. And then you get essentially twice as much data coming out of the other end of the cable. So that's another way to increase your data down a cable. Yeah?
Oh, you said that the plastic ones we use can work for like 100 yards. How long can the glass ones generally work for?
Miles and miles. So yeah, they can go for very long distances. And sometimes the distance is too great even for a glass cable, like if they're trying to send it, across the ocean or something. So in that case, what they do is they put in a repeater. So it would be a little box halfway along, say, that detects whatever signal is coming in and amplifies it, and then sends it out along another cable that continues on the rest of the way. So,
Is there any material that would work better than glass theoretically, but maybe more expensive?
Maybe different types of glass,
Okay.
but I'm not super familiar with that. Yeah, they might be able to put different chemicals in there to increase its reflectivity or stuff. I don't know. Yeah. So that's a little bit about how fiber optics work. So let me talk a little bit about the cables themselves, though. So, and we can pass these around so you can take a look. The cable itself is made up of several parts. So in the very middle is the glass fiber, and then around the glass fiber there is a sort of a layer of insulation, plastic insulation. Actually, let me put this up on the screen so that we can take a look at this. On the very outside of this cable, we have a plastic coating, and that kind of protects the cable from scratches and wear. Then inside of that, we have this sort of fiberglass material that provides some strength for the cable. Inside of that, we have this other orange material. That's another jacket. And then inside of that, in the very, very center, is the glass fiber itself. Now this glass fiber is so tiny, it's nearly impossible to see. So yeah, so we're looking into the end of it there. If I hold this end of the cable up to the light, are we going to be able to? I don't know. But the actual fiber is this little tiny dot right in the center of that whole cable. So just that tiny, tiny dot in the very center there that is the glass fiber itself. Everything else is just shielding and extra material for strength. So you can see it's just extremely, extremely small. We've magnified it a huge amount here, but it's just ridiculously small. So I'll pass this around so people can take a look at that. If you're working with a fiber optic cable in the real world, you're not going to be, you need to connect that cable to something. So that cable would have some sort of a connector on the end. So this is one type of connector. So this attaches to the cable, and then if we look at the end here, you can see there's this big white part sticking out. Again, that's mostly just protection. The actual fiber itself is just a minuscule little part in the very, very center of that. Let's see if we can get it to focus here. There. So briefly, yeah, there's that little black dot. You see that little black dot in the center of the whole thing? That's the actual glass fiber. So yeah, the glass part is just extremely, extremely small. It's just slightly bigger than a human hair. So yeah, it's ridiculous. So I'll pass this around. You can see what the connector looks like. You could take a look at that. And there are many different types of connectors. So that's one type. This is another type of connector. Just depends on what you're trying to do with it. And even fiber optic cables can be bundled up. So this is a bundle of fibers. This is another type of bundle. So these would be used in applications where you needed even more data. So pass those around. So that's what I wanted to say about fiber optic cables. So any questions about that? Okay. All right, so then let's go on and do a preview of today's lab. So the main thing that I wanted to point out was I mentioned earlier in the day that I posted some schematics for other versions of the board. So this is the schematic for the main receiver board. You can see where the test points are. If you have a different version of the board, you can download the schematic for that version. Okay, so this has the schematic for revision 2.1. One important difference, if you are looking at the transmitter, is that in the earlier version, the output, so in the main version, the output came out on test point 6. In the earlier version here, the output comes out on test point 5. Okay, so that is a big difference. So you need to know which version of the board you have in order to know where you're going to measure your output from. You're going to measure that output when you're doing your testing of your board. Okay, so make sure you're looking at the correct version there. So this doesn't want to cooperate right now, but There it is. So, so with this revision 2.2, the output comes out on test point 5 there, and test point 6 is over here. So if you're using revision 2.2, make sure you're looking at the output on test point 5. For 2.3, you look at the output on test point 6. So
What happens if you have like the 2.4 one?
then I will get you the schematic for that one. I believe that the output is still on test point 6, though. Yeah. Yeah. So other questions? All right, then I will take attendance and I'll let you go.